Okay, good evening, students. So last time we have gone through OA1 electric current, right? Probably you know that going through the lecture or rereading of the content we have there uh, is the most famous way of studying, right? But research have repetitively proven that there are some more methods to remember things. This is one of that mind mapping. So you can just prepare this kind of thing. So I have just used only one thing, the color, right? You can use colors, you can use diagrams according to your wish, but this is a proven method to remember things. So I have I'm trying to go through the first lesson today as well, again as a summary. Right? So last time we have gone through electric current. So here the symbol that is I, the unit which electric current measure is ampere. And I hope you can remember ampere is a base unit or not. It is a base unit, right? It is a base unit. So scientific community got together and decided 7 base units. So electric current is one of them. But if you have gone through the definition, that involves some other physical quantities. You know already time, but charge is probably quite new. So we will go to electric charge first. So electric charges are there as characteristics of subatomic particles, even fundamental particles. So electron is one of the fundamental particles. But there are some other fundamental particles which neutron and protons are comprised, which are known as quarks. So there are some other fundamental particles other than electrons as well, like lepton. Electron is a lepton, so there are some other leptons as well. So we'll be discussing about these particles in some other lessons. So it is a characteristic feature like this. If I have taken an object like my calculator, it has a specific mass. You can measure it. Just like that. If I have rubbed this with a kind of a cotton cloth, sometimes this will be charged. And this charge is a characteristic feature. You can't change it unless you have make it a kind of a electrical reaction, right? But if you have taken fundamental particle, you can't change it at all. If you have taken electron, it has that property. If you have taken upward, it has that property like this. Then electric charges are there, not in fundamental laws of atomic levels, sometimes as a big object or big molecules, right? So if you have taken common solid as an example, sodium chloride. Sodium is positively charged particle, chloride ion is a negatively charged particle. So if you have done the electrolysis, you know that sodium ions are moving in the same direction as electric currents. But chloride ions are negatively charged, hence they are moving in opposite direction to the electric current. But what is electric current? Let's talk about that. Electric current is the rate of flow of electric charge. So you know about charges, now you can talk about electric current. So in the case of electric current, Coulomb divided by time, that means Coulomb divided by seconds is the unit. So ampere should be equal to Coulomb per second. So the unit conversion will be facilitated by this text, right? Milli means 10 to the power -3, micro -6 likewise. So you need to go through this again and again, but I have taken that here as well. Then I was talking about electric current and electron motion. Here it is well explained. Electric current is always positive to negative. Electron motion is negative to positive because electric Charges feel forces in a electric field. So any kind of potential, when there is a potential difference, charged particles are experiencing force. When there is an electric field, they are experiencing this. So we know that if it is an electric complete electric circuit like this force is given by the electron. Today's lesson is on that. Okay, we will talk about that in a moment. So these electrons are moving from less potential to high potential according to the potential gradient. No, opposite to the potential gradient. But the potential gradient is from positive to negative. So this is the direction of electric current or conventional current. Right? So there, positive ions are moving in the same direction as conventional current. Yeah. But negative ions are moving in opposite direction, just like electrons. Right? But why electrons are moving in here? Because most of the parts are, actually, almost all the parts made of conductors, right? Electrical conductors. So electrical conductors conduct electricity as electrons. Others are, so metals are mostly conductors, right? There are some other conductors like graphite as well, but mostly metals are conductors. So the electrons are the ones which are making this electric current. So we need to understand that as well. But it doesn't mean that electrons are the only charge carriers. So here we have discussed about negative ions, other than positive. So positive ions are capable of making an electric current. So we still use the conventional current. So in a kind of electrical circuit, how you determine the direction of electric current? This is more important. Even though you should know electrons are moving from negative to positive, this is the most priority, right? Benjamin Franklin is a most priority. So he has decided out of the positive and negative charges, these are the charges which are moving. Still, it is correct partially, but most of the electric circuits are electrons as the moving particles. Okay, so this is the summary. And one more thing, can you see what I have not covered yet? What it is? This? I have no here. I have drawn a mind that if you have read that, you could catch the point where I have not covered yet. What it is? Number of electrons. Yes. So how many branches are there? 1, 2, 3. And this has a connection with the conduction, right? 1, 2, 3, 4. Yeah, those four are branching into some subcategories. So you can remember this as a mind map. So please prepare your own mind map. Definitely that will help. Right? Okay. So in here, number of electrons, they might ask you. So we have gone to a practical observing charge flow. I have shared with some videos with you. I hope you have gone through it. So you can take how many electrons are in need of transferring Q amount of charge. Let's say you have taken 0.5 millicoulomb of charge from one place to another. But they're asking how many electrons are involved in that. So you can take 0.5 millicoulomb, milli means 10 to the power minus 3. So 0.5 into 10 to the power minus 3 coulombs divided by the charge of electron. That is a constant. It is there given in your exam as a data sheet. So you can take that. And this division is the only thing you have to do. So the final answer is you read plus because it's just the number of electrons. This is also mostly constant. That's why I have taken that. So you can develop this into the second stage. Sometimes you can go through the questions and relate the the theory behind those questions to the theory which we have discussed in the study. So you can expand this mind map. So any scope of question you can handle with ease because you have a mind map. You don't need the student book to go through. Right? This is the second part of learning. First, you have to expose yourself to the theory section. I have done that last year. This is the second part. You need to go through it once again. And then one more thing I should share. This is a well-known fact today in psychology. Your memory will go on to very less level within first few days. Right? This will happen. But if you could, so sometimes even though I have taught you 100%, you will absorb only 90. Let's suppose it has 90. The second day, so if you want to the seventh day, because of why I am taking seventh, because on seventh day you are having physics, the same lesson, right? Before that you can go through it. That's why I'm taking. It is best if you can go through it 2 to 3 days after 2 to 3 days. So this will come back to 100%. Why? Because you have your creativity, you have your logical thinking, you can go through the note and absorb the the rest of the thing I have taught you. So you can understand. So it will become 100% of the lesson. Then it will not go through that much steeper. So after, let's say, 21 days from the first one, so this is 1 week, this is 2 weeks. So you can go through it once again. And this level, around 75, is enough for you to face the exam with confidence, right? So at least 2 to 3 times. So if you done that here as well, then another 21 or 2 weeks, right? So if you go through the same theory 3 times more, not only today, so you can remember this very effectively. And also, it is 2 hours when you're studying that in the class, but you can spend only 10 to 15 minutes first day. Then second day and third day, only 5 minutes is enough. You can just skip through it because you know most of the things with this mind map. Right? So theory is not a problem any longer. Then you need to go through different types of questions which you can't cover in a single day. It needs lot of time, lot of practice. So which is we are going to do. Right? Okay. I hope this theory is clear. And if you have any questions, please ask now. Any questions? Tasar, can you hear me?
Yes, sir.
Yes, right?
Yes, sir. Yeah.
Okay, great. Do you have any questions regarding the previous day?
Not here.
No, okay. Yes. How about you? No? These are clear. Okay, then let's move on to today's lesson. That is regarding electrical energy transfer. Can someone tell me what do you mean by energy? Energy. Yes.
It's a quantitative property.
Sorry, could you please repeat the song?
It's a quantitative property.
Quantitative quantity. Okay, they can make
Yeah.
quantitatively, yes. Other than that, okay, can someone help her to bring energy into a big picture? What is energy? Sir? No, it should not be a definition. If you have given a definition, it's okay, it's okay. So, what do you, yeah. Okay, so energy is one of two things in big categories in the universe. So matter is there, energy is there, their relationship is in the space. This is this is everything, right? So we study about everything in physics, matter, energy, and their relationships in the space. Right. So let's let's go a little bit deeper. With energy, what can you do? Work done. Yes, with energy you can do work. Then we can understand energy as ability to do work. Energy is ability to do work. So this energy has different forms. One of the energy forms, each and every of you can tell. Kinetic energy, light energy, potential energy. Kasa, you also can give me an answer. A form of energy. Which is our lesson? Electricity. So electrical energy is also a form of energy. So how can you know it as a form of energy? If you supply energy to a kind of a electrical appliance, it transfers electrical energy into useful stuff. Let's take an example, this fan, which is bothering you all the time. There is a fan which is moving clockwise. If you have provided this with electrical energy, it will transfer this into a form of kinetic energy. Actually, even though you have not gone through it as it is, kinetic energy has two components. Translational, that means on a straight line, and rotation. So this is basically rotational kinetic energy. Kinetic energy, rotation. And which will convert into kinetic energy of wind. Wind is transferring directly downward in direction. Kinetic energy of the air. So you feel that comfortable with that wind. So wind is created by this fact. Okay, just like that, this energy can be transferred. But if you think a little bit deeper, how the fan get this electricity? It is from the mains electrical supply. And how the main electricity supply get the energy? In Sri Lanka, mostly it is no, actually it is 30% hydropower. But unfortunately, it mainly depends on fossil fuel, right? I'll just keep fossil fuel aside and take hydropower to make this simple. So it is the gravitational potential energy of water being transferring into kinetic energy and turning the turbine. So you can understand there is an energy transaction there as well. So what we use here as kinetic energy of the wind is originally the gravitational potential. But how it gets the gravitational potential energy by the way? Water, is water always top in the mountain? No, it is coming down. Who take that water there? It is the sun, right? So water cycle happens. So sun gives us the energy. So that is the actual energy pathway, right? So most of the energy we have here is taken from the sun and we cycle them again and again to different forms, right? Okay, so I'll stop from here. Otherwise we can go to the back. Right, okay. So energy. So this is today's lesson actually. Let me go through the presentation. Electrical energy transfer. That is the lesson. We are in chapter 1. for A, electrical quantities. Under that, electrical energy transfer. Please write down the topic. For A2, electrical energy transfer. Here we have three main learning objectives. First one, we have defined electromotive force and potential difference. Both of them are voltages. Let's talk about voltages today. Then make calculations of voltage and the energy transfer in components. Some of the components give energy to the electric circuit, some of them are using. So these two are called as electromotive force sources and potential difference sources. When we evaluate a model of electrical circuits. So which is also important, but very rarely we are getting questions out of that. But which is also important. Let's go through these three learning objectives. Right, so there is an introduction in your student book for any electrical circuit to be used on. It has to act as a mean of transfer energy useful. So just like any kind of energy transaction, sometimes when you are working, the work done is you are transported from one place to another, right? So how you have done that work in the use of your chemical energy. Again, you can go back and you can go back to the sun, right? So sun is the one which is providing us the energy. So that is a useful work. So we have to talk about that. The circuit must have at least one component of one component that can supply electrical energy. At least one should be there. And it will also have components that transfer this electrical energy into other stores. And at least one of these stores should be useful to its purpose. If you have taken a fan, if it is not transferring electrical energy into kinetic energy of the wind, but light and heat, it doesn't useful, right? It is not useful. So some of the fans are like that, right? Not making any wind, but sound is there, heat is there, right? Okay, so it is not useful. So we use this electrical energy to our stores. For example, in a bicycle light, there will be a cell that transfer electrical energy from a chemical reaction. So chemical reaction has the energy, we are converting that into electrical energy. Then do you have any equation for energy? There are many equations, right? But what is the equation for work? Work done? Yes. Force into? Yeah, I'll just take the symbols on the 4 times. Is it distance or displacement? Because it has a direction, right? So always force into displacement is the best way of taking that. But the displacement should have a direction. Which direction it should have? The same direction as the force. So you can take force into displacement of force. As work done. Force times displacement of force is work done. Then you can understand, in order to do work, you must have the force. In an electrical circuit, which is the force? Electric force. How do you get an electric force? If I had kept this room in an electric field, right? Smaller one, will you feel this electric field? Let's take this metal bottle. Will this fail, this electric fail? What do you think? But if I have made this insulator charged with positive charge, will it fail the electric field? So each and every of these examples, you, the metal bottle, and this may have different answers, but I will simplify this. But you can ask questions from me if you want, right? But I will just summarize this into this insulator charge. Definitely, it will experience. So you can understand if you have kept a charged particle inside an electric field, it will experience this force. So if the charged particle is moving, it has the ability to move because work done is force into displacement. If it is in the same place, but we just started giving the electric field, then it has the ability to do work. That means it has electrical energy. So it can move. When it is moving, we can understand it as the flow of electrons or charged particles, but they are doing work. So that water has not come here to rotate this fan, but electrons are transferring energy upon not electron even. Even electrons are not coming from that hydropower station to here, but energy. So this energy has brought here to make it from. You can understand. Okay, let's talk about these two first. The EMF and PD, but before that, let's talk about this. Let's start writing. It is the introduction. A circuit must have component or components which supply electrical energy. You can copy down this. So I have given you some examples: a cell, battery, dynamo, generator, solar panel. This can supply electrical energy. And the other type of components which are using electrical energy, such as resistors, light bar, toaster. Last time, one of the students taken toaster as an example, so I have included that as well. A fan, etc. And out of these, so these components, at least one of the stores or transfer of energy will be used. Sometimes we store, sometimes we transfer energy. So it should be useful. As an example, a light bulb is generating light as well as heat. But light is the bulbs. If you have taken a toaster, it may produce light as well in the coils. You can see the reddish color. But heat is the useful stuff. So let's suppose there is a component in an electrical circuit, but you can't recognize whether it is a source of electrical energy or a component which is using electrical energy. How can you recognize that? You can think of the other form of energy which is associated with the component. Sometimes which is taking some other source of energy into electrical energy. That is a supply. That is a supply. But some of them are using electrical energy and transfer that into some other. So these two forms are always there. If you have taken a solar panel, what is the energy form which it absorbs? Light energy, photon energy, right? And it is transferring that into electricity. So electrons are moving in circuit. So you can understand it is transferring some other storm into electricity. It is a EMF source. Let's talk about that in the next slide. Right. So voltages. Voltages are two kinds. Some of them are EMF sources, electromotive force sources. Some of them are PDs. PDs means potential differences. If you have taken electromotive force, it always transferring some other source of energy into electrical energy. But if you have taken potential difference, it takes electrical energy into some other state, right? So the electrical quantity voltage is a measure of the amount of energy a component transfer per unit charge, which is the definition of voltage. It can either be into electricity or from electricity. Can easily understand that. So the equation should be voltage is equals to energy transfer divided by charge passed. Energy transferred divided by charge passed. So V is equals to E over Q. Okay, so let's try it. Voltage, the symbol is V and the symbol of the unit also V. Both of them are capital V. Right? So that's why I have it down like this. It's right. Voltage V, capital V. And you can write down the definition. Okay, you can copy down or copy here. Okay, so you can understand the definition of voltage as energy transferred per unit charge. Energy transfers per unit charge. So the equation to remember is V is equal to E over Q. But it is little difficult to pronounce and remember, right? So sometimes you just remember it like that. So that's why I've taken it as E is equal to QV. It's very sweet, so you can understand and remember it very easily. Energy is the product between charge and voltage. So voltage should be energy per unit charge. Can easily remember it that way. That's why I have given you that manner. But if you feel like remembering the equation which is directly taken from the definition, it's okay. So you can go with that. Then let's go through the two forms of voltages. The first one is electromotive force. For a supply voltage, a component which is putting electrical energy into the circuit. In the previous example, the solar panel is the one which is putting electrical energy into the circuit. So you can ask the question from this. How does this component taken that energy. It is not electricity. It is some other thing, right? So this component, the solar panel, taken energy from the solar light, or you can take it as photon energy. So photon energy has been transferred into electrical energy. So then you can easily understand it as an EMF source, right? The character for voltage is electromotive force. So in short, we take it as EMF. It is correct to use even in the exam, EMF, right? And if a cell supplies 1 joule of energy per coulomb, so which form of energy it supplies? Photon energy or electrical energy? Archana? If a cell supplies 1 joule of energy, what form of energy is that? To the circuit. It should be electrical energy. Why? Because it is the one which is making this transaction, and you can't provide photon energy to the circuit. It can't feel it, right? It should give an electrical energy, that is electrons in a conductor medium. If it is not a conductor medium, you can understand it as sometimes it is very correctly mentioned, understood as flow of charges, right? So if you have given an energy, there should be a flow of charge, right? So it can be positive or negative. That's why I have taken that example. So in here, supply energy, if it is 1 joule per 1 coulomb, which is called as 1 volt. So you can easily understand what 1 volt means. That means energy which is equivalent to 1 joule, if the charge passes through the component, is 1 coulomb. 1 joule divided by 1 coulomb is 1 volt. You can easily understand. And EMF can be referred to as energy transferred divided by charge passing through it. So this energy transaction is from other store to electricity, right? So you can copy down this and write down from other store to electrical energy, and you can copy down this as. It is totally up to you to decide which to write in here in this slide. Sometimes you may need explanation for volt as well, but if it is not necessary, you can just skip that part and write out the equation on. Okay, so you can decide what to write, but it is best you can write down here it as some other store to electrical energy. Some other store to electrical energy. Okay, on the voltage, we have gone through this definition. Voltage is energy transfer divided by charge. I have written down in short form. But energy can be referred to as ability to do work. So energy has same as work done, right? Same unit, joules. So we can write down energy equation as force times the displacement of force. And charge can be written as, can you please give me an equation for charge? Lastly, we have got it. Yes. Yeah. But regarding the current, yes. Current current divided by. Okay, what is the definition of electric current? Yeah, current is charge flow divided by time, rate of flow of charge. So the cross multiplication is here. Electric charge is current multiplied by time. Q is equals to IT. Easily, it can be remembered in that manner. Q is equals to IT. So IT is equal to Q over T. So with the time, you will observe that it will go great, but definitely these are to be used in the exam. So we have to calculate that. Right, Q is equal to I. So these two equations can be embedded in this to understand the SI base unit of volt. Because it is a more very frequent question, even in your therapist, that will be there, right? Because volt has no very simple SI base. It is kind of complex. We will just make it simple. So we will get Joule as Newton meter. That's correct, right? Because force is measured in newtons. So I take it as Newton times meters. That is Joule. And Coulomb as ampere seconds. That's correct, right? Ampere seconds. Right. Then you is it SI base? No, you can expand. So how? You means kilograms meters per second square times meters divided by ampere. Can you expand? We can't because it is basic. Base, SI basically ampere and second is there. So you can write down SI base unit equivalent of volt as kilogram should be there, meter square second per second, right? Per second ampere. Oh, I will just say ampere per second. So I'll write down in a moment. Per ampere per second, right? Not ampere per second. Per ampere. So this is not an easy task, okay? But if you have gone through this order one or two times, you can easily pick that up. So this is a kind of a difficult SI based unit overall. Kilogram, I'll check that again. Meter squared. Here, I have made a mistake. Can you catch that? When second is going up, it should be -1, so it should be -3. And per ampere, that's correct, right? Okay. Kilogram, meter squared per second cube per ampere is volt, right? So if this is there in the exam, it will take certain period of time to work on that and take this. So if you have gone through this once or twice or thrice, definitely you will get this in a fraction of time. Please copy down that as well. Okay, let's talk about potential difference. So we have discussed about EMF and let's talk about potential difference. So in the case of potential difference, what will happen? The energy which is there as the electrical store will be transferring into some other. It can be photon energy if I have taken that again as the example. So which is the compound? Which can transfer electrical energy into photon energy. Light bulb, a radiation heater, definitely the radiation is coming out as infrared, comes as photons. So it can be a good source of. So light bulb, definitely. And if you have, yeah, so there is an example. But here we have to ask back, are there any other stores? That question should be there because usually there are more than one one energy store which is being converted from electricity. So if you have taken this fan, you can hear a sound. So is that our purpose? No, our purpose is to take this electrical energy to the kinetic energy of the medium, the air particles, but it is not 100%. Some heat is also there if you have touched the casing, even you can feel a certain high temperature. So heat is there. So it should be useful electrical store. Right? So potential difference can be understood as the difference in voltage in two terminals of an electrical component, and when the charges pass through it, this electrical energy is being transferring into some others. So it can be one or more, very rarely one, right? Most of the time, more than one store is there, right? So are we referring to one other store or all of the other stores as potential difference? It's a difficult question. Even though we are interested in one store, we have to consider all of them because electrical energy has been transferring it into not only one but all of them. So we have to consider all. So potential difference and EMF are two forms of voltage, but EMF referred to supply, potential difference referred to use. So if energy conservation is true, the total energy given should be utilized. So they should be equal to each other. But I will go to Kirchhoff's laws and let's talk about EMF and potential differences separate, right? How they are being equal to each other. But for the time being, let's write down the potential difference. And again, the same definition is there for volt. Component uses 1 joule of energy per 1 coulomb is called as 1 volt. It is potential difference, not EM, because it is the use. And you can write down the equation as well. Okay, right. So let's go through an example. A cell, this is there in your student book, but I'm trying to explain that, and I'll give you some questions as well. A cell transfers 40 joules of chemical energy for every 15 coulomb of electrons that passes through it in order to power an electrical circuit. What is the cell's EMF? So cell is a good example for EMF source because it is transferring chemical energy into electrical energy. So you can use, here I couldn't introduce you this symbol, right? Do you know the symbol? Over here, which is epsilon. E-P-S-I-L-O-N. Epsilon, it's a Greek letter. Looks like E, but it should be, there should be a contrast, right? It's not E, it is rounded like this. If you are writing down E like that, make sure that you are writing square E, square shape E, but this one should be round. So you can easily make them different because E here is kind of square shape, right? Okay. So energy divided by charge is, here they have used epsilon because we have to refer to the EMF. So 40 joules per 15 coulombs. 40 joules per 15 coulomb. So it should be 2.7 volts. So the same methodology should be there in the exam as well. And there's another part. For every 2000 coulomb of charge passing through it, a loudspeaker transfers 18,500 joules of electrical energy to sound and thermal energy. What is the loudspeaker's potential difference? They haven't split this into two as thermal energy and sound. They have taken them together. Can we take them together? Yes, we should take them together because potential difference refer to the all stones of energy. Right? Okay. So voltage in here, they are taken as the potential difference as equals to work done divided by the charge. The work done is not only one store, but all the stores, that is 18,500 joules divided by the amount of charge. It is 9.25 volts. Okay. Let's go through a question. A light bulb transfers 100 joules of energy for every 2 coulomb charge passes through it. If it is 80% efficient for light, what is the potential difference across it? Okay, you can take some time and do this question. First of all, let's write out the equation for potential difference. Potential difference V is equal to work done W divided by half past. V is equal to W over Q. In this question, it is a little bit tricky because they haven't given us the total work. Because when this light bulb is there, electricity is being supplied as electrical energy. But different sources are absorbing energy. But we know that 80% of the total energy transaction has been taken as light. And the light is there 100 joules per every 2 coulomb of charge. Right? Okay. So you can take kind of a statement like this. When 2 coulomb charge pass through the bulb, joule of energy comes out as then the total energy transfer per 2 coulomb of charge. You can take as 100 joules divided by 80 and multiplied by 100. Can't you take it like that? Because 80% will, so if you have taken a certain amount of energy has been transferred, that multiplied by 100 into 80 is light. Light energy. Isn't it? So you need to take the total energy. What you have to do, you have to multiply light energy by 100 and divide it by 80. So this is the total energy transfer per unit 2 coulomb, not unit charge, but 2 coulomb of charge. Alright. So let's take that. So that is 10,000 divided by 80. Still it is in joules. Then you can take PD is equal to total work done. Total work done should be this much. 10,000 divided by 80. Joules divided by 2 coulomb. So you can get the answer in joules per coulomb or volts. It should be 62.5 volts. Right? That is the potential difference. And this is the normal potential difference, right? Across that. So there might be some other components in the same circuit. So the supply will be definitely greater than this. But if it is only the supply voltage and the supply, if the supply voltage is perfect, for potential difference across the bulb and the EMF across the cell or the EMF source will be equal to each other because energy should be conserved. Right? Okay, so I hope you are clear with that. So now, then let's get back to the presentation. Okay, we were in this question, and let's go to the definition of electron volt. Okay, so electron volt looks like, is it a unit of charge? You might think of that like that, but it is a unit of energy, right? So you can use electron volts instead of joules sometimes. What kind of situations? When you are dealing with subatomic particles, you can use electron volts. I hope you have used electron volts in, if you have gone through unit 2, first lesson, topic 3, waves. The last chapter is under quantum physics, and the quantum physics photoelectric effect is there. There we are using electron volts. But I will just introduce you as you are new to this unit, right? Okay. So what is an electron volt? So now you have a sound knowledge about voltage. 1 volt is equivalent to 1 joule per 1 coulomb, right? But electron doesn't have 1 coulomb. It has only 1.6 into 10 to the power minus 19 coulomb of charge. But we make the voltage 1, right? In such situation, how much energy will be transferred through this electron is called as electron volt. Very simple, right? So if I have gone through the equation, you can easily grab that. So voltage is energy per charge. Here energy we have to refer for. So we will rearrange this equation like E as equals to V times E. Simple E refer to the charge of the electron, which is negative 1.6 into 10 to the power minus 19 coulomb. But in this case, we don't consider which direction it is moving, and the name or the sign of the charge is useless, because energy is just a scalar quantity. So we will just take the charge only without the sign, 1.6 into 10 to the power minus 19, and voltage is what? If the voltage is 1, electron will transfer certain amount of energy, which is called as 1 electron volt. So, which is equals to 1.6 into 10 to the power minus 19 joules. See, voltage is 1, E is 1.6 into 10 to the power minus 90. So, the capital E, the energy should be the same. So, charge of the electron will be there as the number in joules, which is equivalent to 1 electron volt. So, here you can see that 1 electron volt is equals to this much of joules. Okay, a small quantity of energy. So, how much work I have done if I have lifted this? Let's take my water bottle is having 100 grams now. If I have lifted this to 1 liter, how much work I have done? This is 100 grams. I lifted it to 1 meter. How much work I have done? Sir? 0.1 joules. Is that correct? So you can approximate G as 10. Is it 0.1? 1 joule, right? Because 100 grams is 0.1 kilogram. 0.1 kilogram into gravitational acceleration is weight. That is 1, because 0.1 into 10 is 1. So this water bottle is having its weight as 1 Newton. If I have given a similar force, but make it move in up, actually we can't move with a similar force, a little bit greater force, so it will move 1 meter in height. So then you can understand that force into that height is the work done by myself. So that is 1 into 1 Newton into 1 meter. 1 Newton meter means 1 joule. So I have done 1 joule. So how many electrons would I need to make that happen? If I was a robot, how many electron volts do I need to do that 1 joule of task? But we have to do that. I had another one which is equal to 1 joule. How many electron volts are there? Which is the other way around calculation. So if you have taken this as there are 1.6 into 10 to the power minus 19 joules per electron volt. You can do this conversion very easily because work done is 1 joule. But we want to convert that into electron volts. So if we have divided this by 1.6 into 10 to the power minus 19 joules per electron volt, you will get the outside electron volts. Okay. Electron volts. What is it? What should be there? You got the answer? Yeah, that is good. That 6.25 into 10 to the power 18 electron volts. Huge amount of electron volts are there, right? So you can understand electron volt is very small energy need. 1 joule is equivalent to 6.25 in electron volts. This is the exact number, the number of electrons in 1 coulomb of charge. 1 over charge of the electron. So here we have 1 over electron joules per electron volt. So this is the energy which I have put in this calculation, right? So you can put it out into the argument. Okay, let's write down how much joules are there per electron volt. You can write down that on the table. So there are 1.6 into 10 to the power minus 19 joules per electron. This is important. And if you wish, you can write out this equation as well. E is equal to V times charge of the electron. Then let's move on to the electrical models. So we know that if you want to describe the arrangement of subatomic particles in the in a atom, definitely you are in need of a model because you can't see that. Still, no one has correctly seen all these subatomic particles and fundamental particles, right? So you can't show. So you have to use a model. So just like that, in a kind of an electrical model, in a kind of an electrical circuit, you can't. So even Benjamin Franklin, who has named the direction of current, conventional current, couldn't explain that very well to the audience because he thought that it was the positive ions moving, but positive charges are moving. But in the metal conducting environment, electrons are the ones which are moving, right? So, time to time when the science update, right? So knowledge show us the direction. Science show us the direction for the knowledge, right? Okay. So in here we are talking about the electrical models. So we do not fully depend on one model to understand anything, right? So because they have their own weaknesses and potentials. When you're taking a model of this skiing area as a model for electric circuit, you can see there is, so if I have taken this a closer view, you can see the ski lift is there where the skiers can sit on, and that will be transported into a greater height like this. Then after that point, they start skiing and they are using different paths to come down. But at the end, they all have the same gravitational potential energy. So you can understand the ski lift as a source of EMF because it puts the gravitational potential energy here. So if you pay attention to gravitational potential energy and think of electrical energy in the electric circuit, you can take the similarity and you can try to understand what is happening in the electric circuit. So just like the ski lift, the battery is putting electrical energy into the circuit. So with this electrical energy, electricity passes through different parts of the circuit. And finally, when it is get back to the negative terminal of the battery, they all have a relatively less amount of energy, like the gravitational potential energy with these skiers, right? So there are advantages and disadvantages of this model. Let's talk about them as well. If you have taken the gravitational potential energy, which is representing electrical energy, it is a good representation because the same thing will happen. Gravitational potential energy is increasing as similar to electrical energy increases through a cell or any kind of EMF source. But if you have taken moving charges in a kind of electrical circuit, which is made out of conductors, mostly it is electrons. But if you have taken the ski area, snowboarders and skiers are there. So you can't take this and this thing correctly into the situation. So these kind of disadvantages are also there. But I'm not going to waste time reading all these and explaining it to you. So please go through it because it is just one model. There can be hundreds or thousands of models to describe electrical circuits. So you can go through this, and there are some checkpoint questions. You can answer them as well. I'm not going to go through those exam practice questions, checkpoint questions today, but I'll show some exam style questions which are coming under this lesson. Right? Next day, I will go through your answers. Please send your answers personally to me through WhatsApp so I can go through them. Then I will, if there is something which is not compatible with the expected answers, I'll teach. I'll take that into account, and I will take a kind of a certain period of time in the future lesson to describe this concept. I'm not going to do that today. But there are some exam style questions, sorry, checkpoint questions which we can go through. Explain how potential difference is different from electromotive force. Okay, so I'll ask like this. So in front of me, there are 3 students online. One student is participating. So, Ochana, could you please start with electromotive force? What is electromotive force? A component which transfers energy from where to where? From another store to electrical energy, or electrical energy to some other store in the case of EMF. I could catch you. Okay, if it is electrical energy to some other, which is called as potential difference, because let's think of this as examples, which is very easy. If you have taken examples, it is very easy. If you have paid attention to the definition and these words, it is difficult. If you have taken a potential difference, a fan will have a potential difference. A bulb, a light bulb will have a potential difference. A computer will have a potential difference. Why? Because it consumes electrical energy and transfer that into some other store. But if you have taken a solar panel, a cell, a generator. So let's take a generator. Sometimes we are using, right? So diesel is being put into the generator. Diesel is chemical. It has chemical energy, right? Fuel, chemical energy. Out of this chemical energy, we produce electricity and operate these electrical components. So there, the diesel engine or generator is an EMF source because it can take the energy of diesel and transfer it into electrical energy. So we call it electromotive force. Let's split it into 3. Electro, what do you mean by electro? Electricity. Motive. Motive means moving, making a motion. Electron motion is referred to as electricity, isn't it? In a kind of a conductor environment, electrons are the ones which are moving. So you can easily understand electromotive force referred to the motion of the electrons. So something which can move electrons should be an EMF source. Which can move an electron? A kind of a component which can transfer some other store into electricity. Then the electrons are moving. So you can easily understand EMF as a source of some other store into it is transferring this energy into electricity. Very clear, right? So if you have taken potential difference for you, okay, so we have gone through it as well, right? So how you just compare them? Electrical energy. So don't use electricity because it's a broad idea as well. Electricity is not referring to energy or charge or current. So electricity is a broad idea, right? Sometimes we use that to power our electrical appliances, so we can refer to power or energy or charge or voltage. It's a broad concept. So you can refer to electrical energy when you are describing EMF or P. They are using, they are searching for that word, energy. Yeah. So if it is EMF, it is putting electrical energy into the skin And P is transfer that electrical energy into some other stuff. This is the difference, right? So you can specially write down and also put this. Okay, let's go through the second question now. A cell provides 76 coulomb of charge with 120 joules of energy. What's the cell's EMF? At the B part as well. So in the first question, they ask the cell provides 76 coulomb of charge with 180 joules, sorry, 120 joules. What is the cell's EMF? So cell's EMF can be taken as energy transfer into electricity divided by charge passing. So they have given it as 120 and 76 is the charge. So could you please give me the answer? 1.59, 58. Have you rounded it off to 58? Yeah, 1.5. Okay, so second part, a lamp carries a current of 2.4 amperes for 5.4 seconds and transfer 120 joules. So the same amount of energy cell is giving and same amount of energy it transfers, the lamp transfers. You can understand that. Then this 120 should include all the tools, not only light. But if it is making a sound and heat, those forms also there, right? And the charge pass, they have not given straight. They have given it as current and time separating. So we need to use this equation here to get that. So it is in amperes, 2.4 current, and 5.4 seconds are there. So what's the answer? Sorry? 9.26. All of you have taken the same answer. A different answer. Let me, sorry. Let me check. 120 divided by 2.4. 9.26. Getting the same answer, right? Good. Yeah, so the calculator identify this as in the numerator. So you have to put the brackets or make it divided. The calculator can't understand whether you have gone to the denominator or in the same numerator. Right? So you need to put the bracket or use bracket. Right? Or put just divide sign in front of 5. So you get the answer. Okay, there are 3 minutes. So it should be 9.26 dollars. Okay, I hope you are clear. If you want, you can copy it out. Okay, so after these two parts of the second question, the third question is, yeah, the same answer I got. The third question is on unit conversion. Okay, I'm not going to do that now. 9.6 into 10 to the power minus 19 joules, you have to convert it into electric volts. And 4.8 mega electric volts into joules, right? You can easily do that because we have done one question like that. And in the fourth one, they are asking you to evaluate this, right? An evaluation of the strengths and weaknesses of the ski area model of an electric circuit. Include discussions of at least the following ideas. What are they? Representation of charge carriers. Complete circuit is needed. And gravitational potential energy, potential as the analogy for electrical energy. The ski lift as a cell. So you have to write down strengths and weaknesses. Some of them are having strengths, some of them are having weaknesses, some of them are having both. So you have to write down both. right? So then you can share your answers with me. So if there is any improvement, I'll let you know. Write a suggestion for a different model. Could you please think of a different model? How about a waterfall? Uh, Artificial waterfall. A pump is carrying water into a kind of higher level and water is picked up. This kind of things you can think of, right? So try to work on that and share your ideas. Probably you will have a better explanation or kind of a model which can explain electricity. Okay, so there are some other questions I have taken it from past papers, but I don't think we have time to go through them. But I'll share these in our group so you can try them as well, right? And next day, I will start from here. I'll go through the questions and go to the next lesson. Okay, right. Before we wind up, do you have any questions? No? Are there any questions? No? Right. Okay. So if you have any, please feel free to send them via group so others also can be benefited out of that. Okay, right. So thank you very much for your time. Let's wind up.